We will proceed with the hands-on session, the demonstration session by our team member, Mr. Manjil Situla. So, Manjil, over to you. You can begin your session.
Thank you, ma'am. Thank you, Dr. Bose, for such an interesting and insightful topic on dynamic meshing strategies and the turbulence modeling in OpenFOAM. So, greetings, everyone. Welcome you all to the introductory level workshop on OpenFOAM. So, again, welcome you all to the basic level workshop in OpenFOAM. So, we'll be in this workshop, we'll be doing a hands-on session on turbulent flow over flapping NACA-0012 Airfoil. So the basic outline of this workshop of this session would be like we'll be learning about basics of the flapping aerodynamics and different parameters, and we'll learn to set up a case in OpenFOAM, and then we'll be doing some post-processing in ParaView. So right now, I have planned to set up a case for the plunging and pitching motion of airfoil, but we will first deal with the plunging airfoil case, and if time persists, then we'll also move towards the pitching motion of the airfoil, and then we'll post-process the results, like we'll be seeing the various velocity contours, vorticity contours, and then we'll also plot the aerodynamic coefficient in ParaView, and then we'll explore some dynamic mesh libraries in OpenFOAM. So Professor Bose has already stated what is dynamic mesh and what are different dynamic meshing strategies in OpenFOAM. So right now we will be mostly dealing with the mesh morphing case. So our main focus will be on the mesh morphing, and there are other different strategies in OpenFOAM which you can always access these different meshing strategies, dynamic meshing strategies. So right now I will be showing you the case for the mesh morphing, which involves a prescribed body motion. So basically, mesh morphing, what does it? It refers to the physical deformation of the mesh. So whenever the boundary moves, then to account for the movement of the boundary or the moving boundary, we need to deform the mesh. And in this, so that is the reason why we need to use dynamic mesh. And for the moving boundary, like suppose an airfoil, so we'll be using the mesh morphing strategy. And the movement of the boundary, that is the moving boundary, can have a prescribed can be moved using a prescribed function, or also can be moved using tabulated data. So there in the mesh morphing, large displacement boundaries, whenever the boundary have to be moved to a large displacement, that will result in low quality meshes. So we need to account for the time step, and the CFL number should also be monitored while we run the simulations, because this will involve the physical deformation of the meshes, which might result in divergence and negative volume cells. Okay, let us see the basic flapping airfoil aerodynamics. So for the plunging and the pitching case, we define a simple sinusoidal motion of the airfoil. So y equals to a sin omega t, that is used for the plunging case. And for the pitching case, we just assign the rotational angle, that is theta equals to a sin omega t. So these will have to assign the movement of the airfoil. So in the plunging and the pitching case, so these are the basic sinusoidal functions or motion of the airfoil, and the which means the amplitude of motion, omega, which means angular velocity, t refers to the time period, and all this is mentioned here. So here in the lower diagram, we can see that the birds flapping mechanism. So actually, when the birds have two strokes, that is the downstroke and the upstroke. So when the bird flaps flaps its wings downwards, it's called the downstroke, and when it flaps upwards, then it's called the upstroke. And these two strokes make a complete cycle for the bird. And we can see that during the downstroke. So let's see the downstroke first. We can see that the velocity, the relative velocity or the effective velocity, is angled at a certain angle of attack, which is the effective angle of attack due to the bird's flapping motion and also the incoming free stream velocity. So we can see that the effective the velocity is angled at a certain angle of attack, and we always know that the lift and drag lift is perpendicular to the relative velocity and drag is parallel to the relative velocity. And we can see that the resultant is tilted forwards due to this unsteady behavior of the airfoil in the downstroke. But this should, for the resultant to tilt forward, we always have to account that the lift, that is the original component of lift, which is L sine theta, should be greater than the original component of drag, that is d cos theta. So L sine theta minus d cos theta should always be greater, so that the lift is, so that the resultant is tilted forward, and then we can generate an effective thrust in the forward direction. So in the downstroke of the bird, they have net thrust production, which will help them to fly. And in the upstroke, like in the upstroke is actually the energy conservation stroke for the birds, so they don't produce any thrust. Only some birds do when they have to maneuver in for different, like the steep climb and other purposes. They in the upstroke also they can produce thrust, but usually the upstroke is for the energy conservation stroke. And we can see that during the upstroke, the lift is also negative. But if the lift is negative, then this might result in the negative height. That is, the height might they might lose height. So in order to reduce this negative lift, what birds do is they adopt various techniques like the feathering techniques, by aligning their wings to the free stream airfoil, so that the effective velocity is aligned with the wings, and the effective angle of attack is zero. So they apply different strategies during the upstroke to reduce the negative lift, and it is basically an energy conservation stroke. But the downstroke is purely a thrust generating stroke and the lift generating stroke. But the certain combination of lift and drag is essential for the resultant to tilt forward and produce thrust. So we will look at this. So there are also different unsteady aerodynamic parameters like the stall number and reduced frequency. So we can see that the reduced frequency is basically the ratio of the plunging amplitude to the free stream velocity. So whenever basically reduced frequency defines the unsteadiness of the problem. So whenever the reduced frequency is high, then that might lead to the formation of the leading edge vortices more quickly and shading from the airfoil more quickly. So this might also result in the decrease in lift, unlike the when the reduced frequency is lower. That will decrease the rate of shading vortices, and then the shading vortices remains attached to the uh, airfoil for a longer period of time. And the another important parameter would be the amplitude, that is h, of the airfoil or of the wing. So the parameters k and h together is described by stall number. So it relates k with h. So the reduced frequency and the amplitude are related together using the stall number, and these two numbers play an important role in the flapping aerodynamics of the airfoil. And we can see in the right hand figure that the vortex pattern behind the airfoil. So in the first pattern, we can see that this pattern is also referred to as the carbon vortex street. So this carbon vortex street is actually a drag producing vortex pattern, because it will oppose the incoming flow and not let the air flow to pass through the propel behind. So this will create more drag. And the second one is the aligned vortex. We can say this aligned vortex street. So this will have no impact on the drag, or very minimum impact on the aerodynamic parameters. And the third one on the C figure is the reverse carbon vortex street. So this will allow the drag to reduce, and this will produce or increase the net thrust in the forward direction, because we can see that the incoming flow is allowed to propel behind. So this is a thrust producing vortex state, the that the reverse carbon vortex state, or RKVS. And this transition from the vortex state, that is the one carbon vortex state, to reverse one carbon vortex state, is influenced by these numbers, that is the Stall number and the Iris frequency, and the combination of the K product of KH, and the individual parameters should also be accessed. Like the product will not on product will also impact these transitions, but the individual effect should also be studied for. And there are many literatures that have studied the individual effect on such vortex state patterns. So these are the formulas of the Stall number and the reduced frequency. Today we will be doing a plunging airfoil case. So the airfoil is at the mean position and it will plunge. First, it will move upwards and then to the and it will have a downstroke downwards. So this is our computational domain. So we have 2D computation. We'll be doing a 2D flow simulation, and we have inlet, all the three sides. That is the three upper, and the front part is the inlet, and we have outlet on the backwards. And we will be also using a turbulent model. So basically, we'll be dealing with the Reynolds number 10 to the power 6, and we cannot use laminar model in this case because it's a turbulent flow. And then we will be using RANS model. We won't be diving into the higher uh, models like the LES and others, certain which are also present in OpenFOAM, but we will be looking at the Reynolds average Navier Stokes model. So it is an AD viscosity model. So we just average the Navier-Stokes equation and then relate the fluctuating terms in terms of the mean flow terms using the eddy viscosity, eddy viscosity. So, and there are basically three important eddy viscosity models, which is the K epsilon model, K omega model, and the K omega SST model. And we will be looking today at the K omega SST model. And these three have different uses and different types of problems. Like in the K epsilon model, it can be used for high RE formulation as well as the low RE formulation. But basically, K epsilon model is used for high RE formulation. That is when the Y plus is very greater in the log law region. And the Q omega model is basically used when Y plus is very less, or we need to resolve the viscous we need to resolve the viscous sob there properly, then we use the K omega model. But these also, they have their own demerits. Like the K epsilon model cannot resolve the like separation and flow separation properly. So when there is flow separation, then the separation point can be predicted wrongly by K epsilon model. So in case of steep adverse pressure gradient, the K epsilon model is less effective, unlike the K omega model, which is more effective in capturing such separation phenomena. And K omega SST model is the blend of K epsilon and K omega model, so it uses a blending function. So basically, it combines these two models. So it can we can use K omega model near the walls and then away from the walls. That is mainly in the turbulent regime. We can use the K epsilon model. So this is the basics of RANS modeling. So you can dive deeper into these topics. Okay, this is our case. So we will be using K omega SST, Reynolds number in the range 10, 10 to the power 6, and we'll be using the morphing mesh. And we can note that there are two important files that are to be present while doing a dynamic mesh simulation, which is the dynamic mesh dict. So and there are basically different solvers, motion solvers that requires different type of files. Like the solid body motion solver will only require dynamic mesh dict file, so that we can input all our motion functions, all our motion libraries in dynamic mesh dict itself. But if we use another solver called a displacement Laplacian solver, so in the displacement Laplacian solver, it solves for the Laplacian equation, and we need the various values like the diffusivity, motion diffusivity constant values, and this has to be provided in the displacement Laplacian solver, unlike in solid body motion solver, which is not required, because this will only this does not solve any equation. This only calculates by the transformation of the points or the transformation of the mesh. So we do not solve any equation, a Laplacian equation on in the solid body motion solver, and the structure is also quite different, that we need an additional file called point displacement for the displacement Laplacian solvers, which is not required for the solid body motion solver. Before that, I want to I want to take you to some websites. So we have the FOSSEE website, and in the FOSSEE website we have the spoken tutorials. So if you go to the FOSSEE website, that is fossee.in, and then go to OpenFOAM. After we go to this page, let's go to the spoken tutorial. So in the spoken tutorial, if you go to the spoken tutorial videos, like there is a good reference for how to set up the case using Turbulent model in the spoken tutorial itself. So if you go to the number 9 and 10 slides, that is simulation of 2D turbulent fluent channel in OpenFOAM and turbulence modeling in OpenFOAM. So if you visit these two videos, there is option for additional reading material. So if you scroll down, then we can see that there is an option called the additional reading material. So if you click this, then you will be referred to this document. So this is an additional reading material for that video, and we can see that how we can set up the different parameters for turbulence model. So I would like you to open this page, and then we can do it together.
Can you please show the path means you have to get that?
It is available in the if you cannot open this page, then I will just show in my system. Okay. Now let's start our case, start with the setup first. So first of all, I would request you all to copy and paste the template case in the run folder that you have created. So if we just let's open our terminal and go to our run folder. So if you can also manually go to the run folder by going into the Ubuntu and then home, and then OpenFOAM, and so I think you know that how to go to this folder, the run folder that you had created yesterday. So I'd like you all to paste the template case in the run folder. So in my case, I think you have all pasted the template case that Ivan had shared in the run folder itself. So if you are facing problems in pasting this template case, then let me know. So we can actually do this from the terminal itself, but this is quite doing it manually will be quite simple. So after you paste the template case, so just get inside the template case. So we have the necessary files for the setup. Now we will be accessing and going through all these files individually. And what do they mean? So first of all, the most important thing for the CFD is the mesh and the discretization of domain. So let's go to the block mesh file first. So it is located in system. or you can also do it directly from the Windows Explorer. So you can just go to the get the template case, then you can go to the system, and in the system we have block mesh dict. So just open the block mesh dict file. So there are the this is our domain, uh, and this is the geometric information of the domain, and this is the geometric information of the airfoil. So the leading edge and the leading edge lies in the 0, 0, and the trailing edge lies in the 1, 0, and the upper part. These are the points. These are all the geometric information of the airfoil as well as the domain. So I will not be discussing detailedly of the how the block mesh file should be set up and how the convention should be used, but there are important topics that needs to be discussed here. So this is so in the previous block mesh files we had assigned the code only the coordinates, but here we can see that we can use the airfoil itself, like that the edges of the airfoil or the time or the uh, STL file itself, to create the mesh in using the block mesh utility. So we can use the edges of the airfoil itself instead of assigning all the coordinates of the airfoil, and we can also a function called the sortable cylinder. So we can also use these two x to have the edges of the cylinder to be used in our boundaries. So we can see that our domain has the airfoil and also has this curved edge. So basically, when we yesterday we did the pipe flow, we just created a square, and then we just used the center point, and then and then use the arc function of the open form. But now we won't do that, because that will be quite tedious task to do for these complex cases. So what we can do is we can define a cylinder, and we can use that edges or the arc of the cylinder itself in the block mesh file. So this is the strategy that is used here. So we can see that we have defined a cylinder type sortable cylinder, and the center point lies on the 0.3, 0, 1 minus 1, 0. So basically the center point it lies on the airfoil. So we can see that the upper point, this it lies on the x upper and x upper of the airfoil. So the center point of the cylinder is 0.3, 0, and it will go from the negative 10, that is the negative jet, to the positive jet. So we can we can visualize this. So this will be our cylinder. So our cylinder will lie on the XY plane, and it will extrude along the Z direction from -10 to +10, and the center will lie on the point 0.3, 0, and the 0.3, 0 in the negative uh, jet and the positive jet. So there are two cylinders on the front and back plane, and it's a 3D cylinder. So yeah, I was about to focus on the project function of the that is available in the block mesh itself. So what we can do is we can project the required coordinates on the cylinder, so that we can use that vertices. So in the previous session, what we did was we assigned the every vertex with the coordinates like in this format, like 1, -5, -0.1, 15. Like in this format, we had assigned the vertices and assigned the numbering of that vertices. But what we can also do is we can project directly these vertices on the cylinder. So what I mean to say is, so these 9, 21, 315, and 012 vertex numbers, we can project on the cylinder and use this vertex number to define this arc, like the 9, 3 arc or the 21, 15 arc. So if we project this on the vertex and we use this vertex to define the arc, then it will be very easy for us to define like the very complex curves or the complex curved edges, instead of like creating a square and then using a center point and then creating an arc. So this is the strategy that is used in this block mesh. So we have projected the required coordinates on the cylinder, and also we can project on the airfoil. So we can also use this curve of the or the edges of the airfoil in the same fashion like the cylinders. So what I've done is the vertex 4, 5. So let me see this. So we can see that the vertex 4, 16, 8, 20, 5, 17, and 7, 19. These lie on the they lie in the airfoil edges. So we can project these points on the airfoil edges and use these vertex numbers to define the arc or the edge of the airfoil. So in this way we have defined the vertex number by using project command. And then what I mean to say is, like, in the edges part. So in the edges part, what we can do is we can project directly these edges on the airfoil such that the edge that we have defined will follow the edge of the airfoil itself, or the air it will follow the edge of the curved edge of the cylinder. So in this way we can define our edges, like to follow the paths, like we followed the airfoil patch edge, and we also followed the cylinder patch edge using this project function. So this will make our work or make our complex geometry simple using this project command. So this is the term that I want to this function that I wanted to focus on. So the other will be the same, that is the convention you use to create the block. So this how to create a block. I think we have seen yesterday how we use the counterclockwise convention to create the block. And another important is also the edge grading. So we can assign a different. We had yesterday seen about the simple grading. Now the simple grading is also used here. So there is also a functionality of edge grading. So we can grade each and every edge of our geometry using the edge grading utility. Okay, this is the block mesh file. So we have our boundary airfoil, which is a type wall, and we have our inlet, which is we have three patches of the inlet. So we have providing groups called the free stream, and these are our inlet boundaries. This is the outlet boundary. This is our and back and front and back are kept as empty because this is a 2D simulation. So these patches have been assigned with the correct which should be assigned with the correct conventions. So another important topic that I would like to focus on is the number of edges and the grading parameters that has to be used in the turbulence modeling. So in the turbulence modeling, as I've already said, that y plus is very crucial factor. Like if we use y plus equals to 1 or y plus greater than 30, then we need to use different turbulent models. So in this case, we'll be using y plus. For our case, we'll be using y plus equals to a greater number that will lie in the log law region. So the document that I had shown you, so there's a very good description of what is y plus and what are the different wall functions that can be used. So you can access these documents. So now what we are doing is we are going in the log law region. So by taking y plus equals to 300, we won't do for the y plus equals to 1 because this will require very fine mesh, and this will take a very long time to for our simulation to run. So we cannot run the simulation here. So we'll be taking y plus equals to 300 in the log law region. And in the log law region, we can the u plus varies with the y plus in the as a log function. So let's see how we can set off the different parameters for by choosing our y plus. So this is we have the formula here for the y plus. So if we choose y plus equals to 300, so we can calculate the first cell height yp. Here also we have seen that it has taken the y plus equals to 200, and then it has calculated yp to be 0.0031 meters, which is the first cell height. So in our case, if we take y plus equals to 300, then we will actually find that yp comes out to be 0.01 meters, which is 10 mm. So we can just use the formula, and this the formula for screen friction factor this is the case for the internal flow, which is a pipe flow. But for our case, which is an external flow, the skin friction coefficient is also quite different. So it is actually there are various empirical formulas for the skin friction factor, but right now we take 0.058 RE minus 0.2 for our case. So with inputting that values uh, in our formula, we can find the YP to be 0.01 meters, which is 10 mm. You can try this on your own. So now after we know the first cell height, what shall we do? So according to our first cell height, we need to, and then what we need to assign number of divisions, that is the in our cells and the grading parameters. So we have a grading calculator called the Blockmesh grading calculator, which is provided by the OpenFOAM wiki. So if you go inside this Blockmesh grading calculator, so here are three important input that we need to enter. So what we know is, so first of all, we need to let us find the total grading that is required. So what we know first is we know the width of the start cell. That is just we found out that it's 0.01 meters, and we know total length of our cell. So we can see that from this graph, because we need to adjust the first cell height from the airfoil. So the upward dimension is 5 meters. So we can see that this is 5 meters in the y direction and -5 in the downward direction. So it's actually 5 meters. So we can just input the value total length as 5 meters. Now, how many cells do we want? Now we need to assign number of cells also. So if we want in this is, suppose in this is like the is 8, 9 or 20, 21, what is, or in this block number 5, what number of divisions do we want? So let's take an arbitrary value now as so we have included 50. So let's take as 50, total length 5 meters. So we can see that the total expansion ratio comes out to be 36.25. So the total expansion ratio here means that it is the ratio of the last cell height to the last cell to the first cell in OpenFOAM. So this actually comes out to be this is the grading that is in the OpenFOAM also. So the grading that is used is the grade, that is the ratio of the last cell to the ratio of the first cell. So what I mean to say is that, so just starting from the airfoil, so the first cell height to the ratio of the near the that is at the upmost cell. So the ratio of the upmost cell to the ratio near the airfoil is taken as the expansion ratio or the grading in OpenFOAM. Okay, I think I made a certain mistake in the 0.01. It's not 0.01. 0.01 meter means, I think it's 10 mm. Yeah, 10 mm. So right. So yeah, we found out the value to be 36.25. So just replace the grading value with 36. Just replace 36. Not just don't take the decimal point. Just we can replace it with 36. Similarly, for all these blocks, so replace 58 with 36. So it's the same in the same way we can calculate this value. So just replace it with 36. So we are doing this so that we can make our first cell height, the first cell in the y plus equals to 300 range. So if we replace all the 58 with 36, so I think why are we doing this? Because we have calculated that for the y plus of 300, the first cell height should be 0.01 meters, that is 10 mm, right? So for the first cell height, for the y plus 300, the first cell height should be 10 mm. So for this cell to be 10 mm, what are the parameters required? So if we have 50 number of divisions in that direction, then our grading number should be 36, so that our first cell height will be 10 mm. So this is the thing that we are doing here. So actually y plus equal to 300 is very larger y plus. So it's always recommended to use in the range 30 to 100 for the high RE formulation, or if we want to do resolve the viscous layer properly, then it's y plus equals to 1. But right now we are doing 300 because the number of cells will also decrease, and this will also take less simulation time, and the cases will be run faster for our case. So after we have done this, so I think our block mesh is ready. Now just we need to, so just go to our terminal and then just run block mesh. So it says the 1974 16 12 03 inside out. Okay. So there is a quite I had made changes to the thing. So this happens when when you assign the block in the wrong direction. So it throws an error called the uh, what we call the block is inside out. So this we need to correct this error. So we can, as I have another file. So this is our 1916. So we need to do in the anti-clockwise direction, 1916 47. Okay, now when I ran the block mesh command, then it showed that the block is inside out. So this will happen when we assign in the wrong direction. So let's correct this. So this is my block that I am assigning the this block is this 1974 is this block. So we can see that I've assigned in 97416, that is the clockwise direction, but actually I need to assign in 191647 in the anti-clockwise direction. So let's do it. 1916 7.
Can you comment this old line and write a new line?
Okay.
Yeah, thank you.
So we are going in anti-clockwise 1916 47. Similarly for the another phase, that is we will be doing 12 15 3 0. 12 15 3 0. So let's see now if it runs, or should I make other changes also? Four, 7, 9, 16. Sorry, it's 16, I guess 17. Okay. Now see that our block mesh is running. So this usually happens when we have assigned the wrong direction of the block. So what I suggest is always if you move from negative to the always move along the positive direction, the positive axis direction. So we are from minus 0.1 to 0.1, that is from negative z to positive z along the positive z direction, right? So if you move from negative z to positive z direction, then the convention will always be anti-clockwise convention. So this is the thing. But if you move from, like, if I had assigned first 0.1 0.1 and then we have assigned minus 0.1 minus 0.1, then that would it would be like we are moving from the in the negative z direction. So that would require all these blocks to be in the clockwise direction. So so always take a same convention while you do the block mesh, so that you won't come into such errors like the inside out problem. So just you move in the positive z direction, that is uh, first assign the low value coordinates, that is the if it's minus, I have used a minus 0.1, you could have also assigned 0 0 0 and 0.1, or 0 0 0 and 0.2. But don't like if you go from 0.2, first you assign the 0.2 coordinates, and then after that you assign 0 coordinates, like the zero plane assign the assign the 0 plane, then this will require the convention to change to clockwise direction. So you can try this on your own and play with this around with these numbers, then you will understand what I'm saying here. Okay, so let's now visualize our geometry in paraview or paraform.
Can you just show the changes that you made again?
So actually, what I made was see, this was the block I that was creating the problem. That is this block, or whenever I would say is the this number one block. So I have defined the block number one with
Yeah.
the faces 7, 4, 16, 19 as one
Mm-hmm.
face, and
Mm-hmm.
0, 12, 3, 15 as another face.
Okay.
Right. So so this is the detailed 3D picture.
Mm-hmm. In the code, what changes did you make?
In the code, I just changed the orientation. So the actually it was what was it? 19, 7, 4, 16.
Just a
It
sec.
was like it was
Okay.
suppose like this in my code, and I made the change to this.
Okay. In the block section, right?
Yeah.
Edge grading. Okay. So I just have one line with hex. Did you add another line?
Oh, what pattern do you have in the X? Like you have these 19, 7, 4, 16,
Yeah. Yeah,
or
and I don't
19.
have the line below that.
Yeah, I added this line.
Oh, you commented out the above line. Okay, okay.
Yeah, yeah.
Okay. And what changes did you make? Only
Just the
uh
orientation I changed.
okay,
Wait, let
just a
me
sec. I
see.
was just 19.
At how many places we have changed this 50 to 36? That simple grading.
Um, so actually, in the Z direction, I changed the number of divisions to 50, and similarly for the Z direction grading, I changed the number to 36. Just in the Z direction, 50 and 36. No, we just have don't want to make the gradings in the other direction.
Excuse me, I'm getting a point merge failure between phase 0 of block 3 and phase 1 of
But
block
there are
4.
some more points where 36 has been made if you see down.
But let me see first. Okay. Yeah, can you repeat it?
I have seen that there are some more places 36 has been made.
Yeah, in these points, like
Below
the
that,
third,
below that, below that.
yeah, in these 50, 36.
So that means wherever there is 50, we can make it 36. Is it so?
No, I think yeah, in the Z direction. I mean, in the so right now, what you might have a question like because we are making the grading in the Y direction, right? But we are assigning the grading in the Z direction. So this might be like you might have such a question because we want to make the grading in the Y direction, but we are assigning the grading in the Z direction in our block mesh file. So this is happening because we are defining the blocks such that this is lies in the third direction. So this will not always mean that the third direction will be the Z direction. So the definition of your block will impact which is are we referring to by this grading. So that will also be the case. So as per your question, so just make changes in this Z direction, like change it in the simple grading, and in the edge grading, change it to 36.
And
Simple.
below that,
Yeah,
that also
all on
36.
yeah 36, or yeah all in the simple grading and in the edge grading, make it 36. We can make it
Okay, okay.
36.
Hi, Manji. I have in the text. I have message. I have message. Could you please see?
Okay, can you just I only had made changes to the first block in this way, 1916 47 12 15 30. But let me see the template case that I had sent you. Well, is it different? Template case. Yeah, it's the same case. So okay, I'll show you from here. So it was this was the template case that I had sent you. So what I made change was I commented out the first block, and then I changed it to 1916 07. So you can repeat with me on this. And the second change I made was 12 15.
4, 7.
So this was the first change required to correct the orientation of our block. And the second thing that I had changed was the grading. So we had assigned 50 number of divisions. So as I showed you in the block mesh calculator, so we changed the this 38, the 58 to 36. So in the age grading, in the simple grading, we changed this number to 36. So everywhere there is 58, change it to 36, not the 51. It's just the 58. Replace it with 36 to match the grading. 36. Now, if you do this and run the block mesh command, then this will run. Okay, I hope you are following me. If you face any errors, then let me know again.
I'm not using OpenFOAM 9. I'm using OpenFOAM 2412. So if somebody else confirms that it works for them, then it's fine.
Yeah, this is written for the OpenFOAM 9 itself, version 9. So this is
And
working.
anyone else confirm that it works for?
Okay, has anyone like facing problem? Is other also facing problem in block mesh?
Yeah, I'm also facing problem. It's showing fatal error, probably due to inconsistent grading.
So I think like you have made changes in the grading in different places. That might also cause that problem. Like
Okay, let me check it once again.
okay, while we do that, we can move through some explanations because we will be. Has anyone like run this and without any errors?
Yeah, the block
Okay,
mesh is running fine now.
okay, fine then.
Yeah, I can also see
Yes.
the paraview thing.
Okay, so let's now move on because we need to run the simulation also, and we are low on time. Okay, fine. We can so after you run the block mesh and just run Paraform and see the mesh. So if it is right or if it is okay. So after that, let's move on to setting of the dynamic mesh. How do we set dynamic mesh in OpenFOAM? So let me go to my case. So it's the template case. And we can see that the dynamic mesh dict is located in constant and dynamic mesh dict. So if you open this, so you can see that there are different now. I will again take you to some of the different libraries that is available in the open form for dynamic mesh. So just go to your Ubuntu and then go to your OPT and then OpenFOAM 9. So here is the installation location. So this is the installation directory of your OpenFOAM version 9. So if you go to SRC and then you go to dynamic mesh. So there is a folder called dynamic mesh. So before going dynamic mesh, so we have dynamic mesh and dynamic FV mesh. So the first library that we okay, now let's see. So we have called a library called dynamic motion solver FV mesh. So if you go inside that dynamic FV mesh and dynamic motion solver FV mesh, so if you go into the source code, then this is the source code. You can to understand this, you should have a understand and modify this. You should have a good understanding of the C++, and then we can see that what I will only try to explain some basic things. What are these inputs and what inputs are required in these files. So we have assigned the dynamic FV mesh, dynamic motion solver FV mesh. This is the first class. So this and if you go into that source code, we can see that it is calling for motion solver this class and the class called motion solver. So and this is also required. So we now see that after assigning the first line, then we have assigned this is the library that is already compiled, that is .show files. So this we can also extract the compiled cases already using the .show files. So we have also called .show this is the library FV motion solver. And what we could see from the source code is that it is asking for motion solver. So we can see that motion solvers should also be assigned. So now where do you find motion solvers? So if you go backwards, then there is also another folder called the dynamic mesh. And dynamic mesh, if you go down, then you can see that there is a folder called motion solvers. So just get inside it. And after you go to the motion solver, so just click on the displacement solver. So we are dealing with the displacement solver right now. There are actually two types of that might be displacement solver or can be a velocity solver. So displacement solver, it actually calculates the displacement of the mesh, and velocity, it will calculate the velocity of the mesh and then include in the governing equations. So actually, from displacement also we can calculate the velocity, but velocity solvers directly calculate the velocity and include them in the governing equation of the dynamic of the that is a mesh velocity we need to assign in the governing equation itself. So if you now go to the solid body, so we are doing the solid body solid body motion solver. So if you go inside solid body, so you can find that there are different type of solid body solvers. So now we are used is interpolating solid body motion solver. So we can see that motion solver that we have used is interpolating solid body. So you can also have used other solvers for this for the same case. So that depends on what type of solver you want to use. Now after get inside body motion solver and just go inside the source code. Now you can see that what does it ask for, like so you can see that it's lookup, that is it, the input that are required in the interpolating body is patches. So we need to input the patches, we need to input the coefficient of gravity, we need to input the inner distance, outer distance. So this should be inputted in the interpolating. These are the parameters that the interpolating the source code asks for. So we have inputted the patches, this coefficient of gravity, inner distance, outer distance, and the another important is solid body motion function. So we also need to input the solid body motion function. So where can we find the solid body motion function? We can find it. So you can see that here is a folder called solid body motion functions. And you can see that there are many type of motion functions. So it is a prescribed body motion function. So if you want the airfoil to move in a linear motion, or you want it to move in oscillating linear motion, oscillating rotating motion. So these are the different motion prescribed body functions that can be assigned in the motion functions. So what we have used here is the oscillating linear motion. So you can see that we have used oscillating linear motion, right? So this is the so let's open the oscillating linear motion source file. So we can now we can observe that what is the so formula it is used, that is it is using this formula, that is displacement equals to amplitude into sine omega t, that I had showed in the first slide, that is how the sine we are modeling the sinusoidal motion. And after this is the formula, and what does it ask for? It asks for, so it's just input, we need to input the amplitude and omega. So we have what we have inputted is, so in the oscillating linear motion, we have chosen the motion function as oscillating linear motion, and the oscillating linear motion coefficient, so we need to input amplitude and omega. So in this way, by looking at these codes, we can see what inputs we need to provide in the dynamic mesh dict file. But already this is available, so you don't need to like revisit the code, and you just can copy tutorial case and then just edit these things. But if it is not available in tutorial, then you need to go to the source code and then look what the code is asking and what input are to be made in these dynamic mesh dict files. So interpreting body motion solver is what it does is, so it helps to assign the inner distance and outer distance. So what does it mean is, inner distance, let's suppose that near the airfoil we don't want deformation, because if we have a heavy deformation, then that might result in low quality meshes, and the solution might be inaccurate, or might also result in divergence. So what we do is, in this inner distance, so let us suppose in for example, as an analogy, so let us suppose that this is a radius, we have a radius of 0.01 meter, and in this radius of 0.01 meters or something like that, there is no mesh deformation, and the mesh that is it the mesh the mesh won't deform in this region, in that radius, and in between this inner distance to outer distance there is actually mesh deformation, and from the out of this outer distance the mesh is static, but inside the inner distance the mesh will move, but it won't deform. So that the mesh will move with the airfoil, the moving boundary, but it won't deform or distort. Unlike in this between these distances, the mesh will deform. So we can also see after we run this case. So how you can also check out, like within the small radius near to the airfoil, the mesh will only move but not deform, and up and far from that it will deform in between these distances, and again at the far end towards the boundary patches, there is no deformation. So interpreting solid body helps us to define such values, and it is very important when we are doing with large displacement problems, because in large displacement there will be involved large mesh movement, and this might cause heavy deformation of the meshes, leading to inaccurate results. So another thing that we now oscillating linear motion coefficient. So we need to input the amplitude and omega. So we are inputting the we are moving the airfoil in the y direction. So basically we are inputting 0.25 as an arbitrary value, not arbitrary, but we want to make the product of amplitude and omega as 1, that is 4 into 0.25. So this makes 1. So omega it's written as 4, so we can input these values can be altered according to our problem. So this was dynamic mesh file, dynamic mesh dict. Now another important is the momentum transfer. So we can see that we have used the Renz model, and the Renz model uses q omega SST. So that's it. Now after we have also set the kinematic viscosity as 10 to the power minus 6, because we want the Reynolds number to be 10 to the power 6, and our free stream velocity is 1 meter per second. So this we can calculate and put these values in our equation in our file. So let's now go to the boundary condition.
Can you once again say where is the momentum file? And I couldn't find it.
It is located in constant
Oh,
momentum transport and
okay.
transfer properties.
Okay. Sir.
Okay, fine. So here we have created there is also, I think in your template case also there is a folder called 0. For now, just delete this folder. This is not required because we will create it later. So just you can delete this 0 folder. We only need 0.original folder. So we will make changes to these folders. So let's start with the velocity boundary condition. So we have set the velocity boundary condition to 1 meter per second, and the velocity boundary condition, the important velocity boundary condition that is required in the moving boundary is the moving wall velocity. As Dr. Bose had stated that this moving wall velocity is important for the dynamic mesh moving boundary. So what moving wall velocity is quite different from no slip boundary condition, because in no slip boundary condition, the wall will have zero velocity. That is, the wall will, even the wall is moving, it requires the wall to have zero velocity. But using moving wall velocity, it is not the same case. Even if the wall moves, the relative velocity between the upper layer of fluid above the wall and the wall, the relative velocity will be zero. But the wall will have velocity according to our prescribed body motion. So the relative velocity will be zero, but the wall will not have a zero velocity, unlike in the no slip case. So this is only the important boundary condition in the U file. So we have assigned the moving ball velocity, and then inlet as a we have inlet as fixed value, that is 1 meter per second. So we have using inlet as 1 meter per second, then outlet will be inlet outlet boundary condition. So inlet outlet boundary condition will, if the flow reverses back, then it will take the boundary condition of the inlet. But if the flow does not reverse or recirculates, then it will actually use the zero gradient boundary condition. So this inlet boundary condition does that. So front end bank will be empty because it's a 2D case. So this is our U file. Similarly for P file, we have used zero gradient boundary condition, and the outlet we need to use fixed value, because in the velocity boundary condition we had used outlet as a I guess inlet outlet or zero gradient boundary condition. So in this case we need to alter these things. Now the important three parameters for the turbulence modeling is the K, nu T, and omega. So let's visit these files. Okay, so this is our K file. So we are, here is a, I had referred one document previously, that is turbulence modeling in OpenFOAM. So here is a detailed description on how we calculate these different parameters. So we can see that how we calculate K, how we can calculate omega and epsilon omega for our cases. So you can refer to this document on this calculation. So I won't go detail on these calculations. So what we do is internal field, we set it to the 3.7 this value based on this formula. This is the formula that is used, and we have set the turbulent intensity to 5%, that's 0.05. So you can set this value as per your flow problem. And the important thing that we need to notice is we have to use wall functions, because our y plus is in the log law region. So if we have a y plus in the log law region, then we need to account for that, we need to use the wall function. So we have used the airfoil, we have used the KQRL function. So you can also visit what KQRL function is. So the equations involving this. So this is so in order to visit these codes, where are they available? I'll show you. So just go to SRC folder. So if you go to the SRC folder, then there is a folder called momentum transport models. So go to momentum transport models. So you can see that there are different type of momentum transfer model available here. So if you want to go for eddy viscosity models, or you can explore these folders. So so RAS models. So we have K epsilon, K omega SST, all these models that are available for the RANS model and for the LES model. So these are different types of models. Okay, so if you now go into derived FB pairs fields, there is a folder called wall functions. So these are the available wall functions in OpenFOAM. So out of which we have used the KQRL function. So if you want to know what is KQRL function, so you can just go into these different source codes and how what are the equations involved in the KQRL functions and how are these are already set up in the source code itself. So we don't have to set our own or write our own code. We just have to refer to that syntax or that library, and this will automatically take that from the uh, code. Okay. So I think we have set up the value for k. Now we need to set the same using the same method for the omega. So for the omega, we use this formula, that is the k 0.5 c mu 0.05 into L, which is L reference length. And using this formula, we get the value as 0.11. So you can try this. So you'll get the same exact value. And we also need to use the omega wall function. So which is used here for the, because I have already said our y plus is in the log law region. So nu t, it calculates from the k and omega value itself. So we don't have to define anything for this. So, but we need to define the wall function, and it is the calculated boundary condition. So it calculates from the available k and omega. Or there, and there is also there is also an equation involved for the calculation of nu t. So this is this we can see inside our source code. So you can go through their source codes and then see how it is calculated nu t. So it can calculate one condition. So it relies on the value of k and omega, and there is an equation for that also. So you can see that in this file. So we can see that omega is calculated in this formula. So see, this is the formula for omega, and nu t is for the k epsilon model, it's c mu k square by epsilon, and for the q omega model, it's this formula. And the effective velocity is the combination of laminar viscosity and the turbulent viscosity or the eddy viscosity. So this in this way, it will calculate the effective velocity also. The OpenFOAM code does itself. So this nu t is the effective viscosity. So it just this is the turbulent viscosity, but the effective viscosity is calculated by the OpenFOAM code itself by adding nu t plus the laminar viscosity. Okay, so these are our basic setup. So we have the boundary conditions ready. So now let's dive into the all-around file. So if you look at the all-around file, so this is our all-around file. So we'll copy the original folder to the folder called 0, and we will be using block mesh, and we will be using decompose pass. So we will be decomposing our processors and run this so t log dot block mesh. It helps to write the block mesh in the as a log file, so that any error occurs, we can see the log file itself. So this is for error tracking or debugging cases. So and then last we reconstruct the reconstruct part. So let's now run our case. So just you need to type, go to your template case, go to your terminal, then type all run. So it says permission denied. So this might help. Okay. So if you also, I think you won't face that problem, permission denied. So you can run this case. So just type / all run.
Sir,
Dynamically.
getting permission denied, sir.
Okay, if the permission denied, then just type chmod +X. This is the, so this will help to provide permission to the all and anything that starts with all, and asterisk means anything that starts with all. So all run all clean files. So this will have to provide permission to those files.
Yeah. Will you be showing how to monitor the residuals as well dynamically?
Okay. Let's see. Okay. Okay. The important thing that I forgot to mention was we have control dict also. So I have not explained about the FE schemes and FE solutions, because these are numerical schemes, and you can learn this on your, that this requires different changes. So you can play with these different numerical schemes and check your solution. So this will also affect our solution accuracy and all sort of our solutions. So FP schemes and FP solution, these are the two important files. So how we solve P, how we solve our U, K, omega, using what type of solvers are required to solve these. These are available in the FP solutions. And we are using the pimple form. So pimple correctors will be used, and how many correctors we need to use, and the relation factors. So these are all available in FP solutions, FP solution file. So you can check that. Okay, I was talking about control dict.
After running all run, what is the expected output?
Okay. So in our all run, this is our script. So in our all run, what we have assigned this script with, these commands will be run. So first of all, it will copy the original to 0 folder, because 0 folder is required because as initial folder, initial time step, and then after it will run block mesh, then it will run decompose path, that is decomposing our processor, then finally it will run the pimple form solver. So this is our flows, that our solver that will solve for the governing equations and find the solution and calculate the solutions. So these will run, and we need to expect the solution of our. So instead of running pimple form in our command in our terminal, we are running it with the through all run file as a script file, and after that, at last, it will reconstruct the.
So just in one file, all the things can be written. An execute function,
Yeah,
int main, int car,
yeah, yes.
no time selected. I have pasted my this warning in the chat.
Actually, have you run your simulation, because reconstruct part is at the last part of the last command. So it's just simulation complete.
Yeah, I have run earlier also that block mesh and everything it successfully.
Okay, so is the simulation complete or getting time? No time selected. So actually, it's a warning that will not create a problem in our solution. But because at the end we have ran reconstruct par, that is it will reconstruct from the decomposed state decomposed file. So it will reconstruct into the single time step. So while we decompose the cases, then the solution will be decomposed in various number of processes, and we need to reconstruct it again into a single folder or into a single time step. So let me see if this will. So if this warning will create a problem later while reconstructing, then let's see it. So right now we
Then
have.
we can directly go to now ParaView or something.
Yeah, we can just. So if you run reconstruct par again, then what it will throw the same error, or what will it do? Well, let me see. Let my simulation complete, and we'll see that.
But your screen is running for longer time. Mine is done in just 10 seconds.
10 seconds. No, actually, I had done it is for 3.2 seconds. So we can see, okay, I was explaining the control dict. So we can see that our end time is 3.2 second with our delta t as 1e minus 5, and write control as a stable runtime. So it will have to, we can write time steps according to our need. That is, we can write as an interval of 0.05. So we'll write 0.05 and then 0.1, 0.15, 0.2. So in this way, we can write our time steps. So we can see that in our processor also 0, 0.1, 0.2, and 0.05 is also. So in this way, 0.
So
Yeah.
if I run it separately, it's giving me floating point exception, code dumped error.
How many processors have you made changes to number of processors, or
No, sir, nothing. Instead of all run, I just gave separately the commands and it's giving me error.
so do you ran this code, right? All run.
Yes, sir, I ran that. That also
What
gave me warning, the same warning.
What was the error?
The warning that was already discussed.
Okay. Okay, let me see if I have also the same one. So okay, let's because if it was an error, then we should have resolved that, but we can move on if it's just a warning. So because our reconstruct par is working fine. So if you see that my case is reconstructed, right? So if you just type if what we need to type is reconstruct par. If you have not reconstructed, then just type reconstruct par. This is the command to reconstruct the different from the decomposed state. Okay, now let's visualize our result in ParaView. I think the simulation is complete. So this is our control dict, and it's okay. Somebody had asked to. So we have also what we have done is we have plotted our residuals also using the function. We have the available functions to plot residuals y plus first coefficient in control in the open form itself. So we don't have to write our own functions to plot these values. So these are already available in open form to compute residuals. So we can see that. I think it's in. If you have run the simulation, then just go to post processing. So post processing. So you can see that there are three folders called first coefficient, residuals, and and then there is a folder called for y plus. So in order to plot residuals, what we can plot using uh, GNU plot. So there is .dat file. So you can plot it using Excel or anything, but if you want to plot it as a live plot while the simulation is running, then you could have used a GNU plot for the method. But now our simulation is complete, so I will show you how we do that. WSL. So if you go to so we have a file called residuals.dat. So just open GNU plot. So after you open GNU plot, so you can plot using this command residuals. So is the name of the file.
Sir, for the post processing, it says no such file or directory. Sir.
So because of that foam warning and reconstruct par error, there is no post-processing folder that we are creating. The simulation hasn't run.
Let me check. Okay, have you deleted the zero folder that I had said or something? So at first I had sent the template case with the zero folder. So you can delete that zero folder and then try. So okay, so this was a template case. So just remove the zero folder. I think I have
36. It was 36.
so that my original drawn folder got replaced while I was extracting that. So I need to run the simulation again. Okay, this was our template case. So I asked you to delete the zero folder. Now just open, so now I'll try to run this. Let me see if there is such warning. It says no processor directory is found. So do some.
In the blocking list, that 36 number you have typed 5 times instead of 4.
Okay. Okay, fine. So I just pasted from the one that was running. Okay, I think if you have problem, then we will discuss this later. But right now, for the template case that
Yes,
I
yes.
sent you,
Yes, we can
it
take
is
up the
running.
questions. I mean, whenever we have the question answer session today, it's from 5:15 to 5:30 schedule. But we can also drag for 5:30 to 5:45 if needed today. Okay, so please continue.
Okay, ma'am. Okay, so I was showing how to plot the residuals. So I'll show how to plot residuals, and then we'll move into the post-processing part now. So you can plot residuals using GNU plot. So what are the residuals actually located? It is located in the post-processing part. So in the post-processing, so if you go to the residuals, and there is a file created called residuals.dat, or it will if you go inside it, so there are different according to as per time it will plot the pressure residual, the velocity residuals, k omega. So if you want to plot this, then suppose this is the velocity is in the third column, time is in the first column. So you need to assign, you want to plot like using, so if you want to plot x-axis as time, then just one. If you want to plot velocity residuals, then it is in the third column, so just do it 1:3. So it's in the first column 1:3, and width line. So in this way, you can plot using GNU plot. So and you can plot this as a live plot while the simulation is running, but actually our simulation has completed. So it is the residuals. We can see that is also going to a lesser converging values. So this is the way you can plot the residuals. If somebody had asked how to plot residuals, so you can do this. There is also another way to plot the residuals using pipeform plot watcher, and you need to write a different residual script for that. So the residuals, this is the we are using this as the available function in the control dict. So we can the in the OpenFOAM itself there is available function for to calculate the residuals. So we have used that. But there is also, and we can also write a script ourselves so to plot residuals and use GNU plot to plot that. Okay, now let's pair view. Let's see close to SR result in pair view. So let's run paraform. Now let's run paraform built-in. So this will help for, so if the cases are very heavy, then sometimes paraform crashes. So you just need to run paraform built-in for that. So if you run paraform built-in, just click apply. So you can see that our simulation has run. So let's go to the now let's plot let's see the velocity contours. So this is our velocity vector. So I think you can plot different post-process different things using the paraview. Like you need, if you want vectors, then you can plot vectors. Like there is an option called or glyph. So if you want to plot the vector, then you can plot using glyph also. So just refine it. So you can visualize the movement of the vectors. So you can see that in the recirculation or when the flow recirculates, the vectors just change the direction. So we can visualize the direction using the vectors tools available in the paraview. So there are many post-processing we can do by using the paraview. So the important I want you to show is now how to plot vorticity and all the things in the paraview. So the main because in the flapping airfoil, the vortex generation vorticity is very important. So just go to filters. Where there is a gradient of unstructured data set. Let's see that. So go to filters, alphabetical, and gradient of unstructured data set. So there is here gradient of unstructured data set. So go to it, and then you need to change the scalar array to U, because vorticity is calculated from a U, that is 2 omega U something. That is the, in this way you calculate vorticity. So we can toggle the set advanced settings. So here is a small rear option here, that is the setting options. So just click on that, toggle advanced properties. So if you toggle that, then there will the drop down will open. So you can see that what we want to compute. We want to compute gradient, we want to compute divergence, compute vorticity, and so on. So we want to compute vorticity for now. So just click on compute vorticity, click apply. Now you can go to your go to the drop down and you can select vorticity. So in this way we can compute vorticity. So you can customize the range. So it's very large. So if you want to make it visible, so you can customize the range on yourself. So in this way we can compute vorticity using the gradient filter available in paraview. So I think this so you can post-process the results different values, different parameters on your self because we have we have run the simulation, so
Yeah.
you can do it on your own. So I think we can end the session here for this. So thank you everyone. Yeah, thank you everyone for joining, and
Thank you. Thanks a lot.
Thank you, Manju.